Good.
So before we get started, I heard that some of your fellow students found a phone in the men's bathroom that was turned into the physics office down on the ground floor. So if you lost your phone, it may not be someone in this room, but if you did lose your phone, it's down in the physics office. Ready to get started?
Yeah.
Okay, so we're happy to start another series. Lara Anderson from Virginia Tech is going to be talking to us about tools for string geometry and string compactifications. Take it away.
Thank you. So congrats on making it halfway through this course, guys. This is, as other speakers have said, this is a lot of material. So I'm really happy to be here and to get to meet all of you. I've actually never been to TASI before because I did my PhD in Europe, so did European summer schools. But I would like to echo something that Matt and others said, which is that this is a great opportunity to meet people that you're going to be hanging out with, working with, writing proposals with, writing papers with for a long time. So I hope that you guys are using this time well and having fun so far. I am super impressed with Boulder. This is my first time here, and the mountains are amazing. So I'm expecting a baby at the end of the summer, so I'm not going to be doing any hiking this trip, but I hope that you guys have been. I hope you've been enjoying it. So this is a pretty broad title that I've put up. I want to show you a variety of tools, and I want to start with some motivation about why these particular, mostly mathematical tools are of interest for field theory, and specifically for string theorists. So the things that I want to begin with are some motivation. And the basic motivation is the question: what effective theories, field theories, in various dimensions can arise from string theory? Now this is, of course, a super broad question, but one that we'd all like to know the answer to. The context that I'm going to be trying to address part of this question in is specifically in the arena of dimensional reduction. So I want to look at complete string theories, if possible. They're perturbative, closed string, open string, non-perturbative degrees of freedom. I want to be able to look at a complete string theory in some family, and I want to ask, how do I begin with a higher dimensional theory in 10, 11, 12 dimensions, whatever it is that I'm working with, and how do I get down to lower dimensional theories? And of course, the interest for me here in this question of what can I get from string theory is I'd like to be able to fill out a Venn diagram that looks something like this. QFTs in various dimensions, string EFTs in various dimensions, and then perhaps a subset of so-called special theories. This depends on what we're interested in. So special theories might include, for example, phenomenological applications. Maybe I want to understand how to do models of particle physics in 4 dimensions. That's something that I'm interested in. Maybe you're interested in string cosmology. You want to be able to write down inflationary models. Maybe condensed matter physics. Maybe conformal field theories in various dimensions. But the question is, what does this look like? So is it true that you can get basically everything, any consistent quantum field theory in any dimension, from a string theory of some persuasion if you try hard enough? Is there actually constraints that tell you that UV completions only exist for special effective field theories? And if you have a particular theory that you would really like to get, say this is the standard model of particle physics, does it actually exist within string theory? So this is a question that matters to you if you would like to use string theory for various specific applications in specific dimensions. So really what we're going to be trying to do, specifically in this process of dimensional reduction, I'm going to be looking at 10 and 11 dimensional theories and reducing to lower dimensional EFTs. And in this framework, in order to try and address the question of what field theories arise in various dimensions from string theory, because I am reducing dimensions, I am integrating out various degrees of freedom of the theory that depend on compact extra directions. What I really want to be able to do is to see how far I can go replacing the question, which EFT with which geometry. Where here, what I mean by geometry is a compact space that helps us get from 10 or 11 dimensions down lower. Yeah. This is a great question. You could certainly consider non-compact theory. So I should say, by the way, this is about starting with a 10D theory. This is its spatial dimensions, and I want to get down to a 4-dimensional or 6-dimensional, lower dimensional effective field theory. So I'm not talking about compactness of the moduli space or degrees of freedom in the theory overall. You certainly could ask the question with non-compact geometry. So you could say, I'd like to just, say I start with a 10D theory. I want to stick around in 10D and ask what I can do. That's a good question. Good question. So I am actually going to be interested in complete theories that I get. So I'm not going to take a decoupling limit. I want to say string theory is a theory that is coupled to gravity innately in its fundamental formulation. In principle, I want to see what that coupling gives me in terms of constraints. Now, you could, of course, decouple and just consider open string degrees of freedom. That's a fair thing to do. I'm going to try and take things in as complete a package as I can. OK. So, of course, this question has a lot to do with questions in the so-called landscape, which you're going to hear more about from Professor Waffe in the next couple of days. And there's lots of great questions one can ask. There is a loose tendency within the idea of this landscape of possible theories to assume that anything is possible. Anything goes. And although there is certainly a heck of a lot in the space of string compactifications, this is very, very big indeed. You've heard the number 10 to the 500 floating around in various places. What I want to argue is that that viewpoint of assuming that you can just get anything forces you to miss potentially important structure. And you'll hear more about that from Professor Waffe in various contexts this week too. So my view is not anti-landscape, but that I want to see how can I possibly constrain that landscape, what can I understand about really how in various lower dimensions string theory is different than just quantum field theories or quantum field theories coupled to gravity that I could write down. So that's the very broad motivation. Now specifically, what am I going to tell you? These lectures, what are we going to do? So what I want to give you a feel for is I want to explore the interplay between geometry and effective field theory. So I made the claim that a lot of features of effective field theories can be translated into questions of geometry that you're using in dimensional reduction. I need to argue for you, I need to illustrate how that comes about. The other thing that I really want to understand is there seems to be evidence within large classes of string compactifications that in fact, rather than anything goes, you get a quite bounded, finite set of possible theories. So I'm interested in those bounds. I want to understand how can I constrain the geometry that could arise and how can I use that to constrain effective field theories. And I may also be interested in ways that different geometries or different effective field theories can be linked. So broadly, string duality as it interplays with geometry. Okay, so that is a pretty loose set of statements. Let me just say a little bit about motivations in these questions. I can tell already I'm not doing ideal board placement. We'll try and not cover up what I just wrote quite so fast in the future.
The third one doesn't move, just so you know.
That one I got. This is good. Somebody can tell me the algorithm of 1 versus 2 versus 3 next Okay, if I haven't figured it out by then. All right. So what we want, optimistically, is, of course, we'd like to see things like patterns, constraints, and perhaps, if we're feeling super ambitious, even predictions from string theory about effective field theories in various contexts. For example, in string cosmology, in string phenomenology, in particle physics, etc. So I need to get started illustrating this somewhere. So to begin, we'll illustrate with a heterotic string dimensional reduction. Why start with heterotic? Well, there's lots of other interesting string theories too. Heterotic is interesting because you can say quite a lot about the structure of geometry and its interplay with field theory before you even get to non-perturbative degrees of freedom. So even within the perturbative theory, there's a lot of structure of different parts to geometry that can speak to each other. The tools I will emphasize. I'm just going to illustrate this with heterotic, but the tools will be more general. And I'll try and highlight for you where a lot of what I'm saying applies equally well to M theory, type 2 theories, etc. Just a quick caveat, of course, as other speakers have mentioned, there's a wide range of backgrounds in this room. So some people do the type of math that I'm about to show you all the time, and they're very familiar with it. Some people have never seen any of this before. I'm trying to strike something of the middle ground. What I'm trying to do is not make these relatively self-contained and not assume a lot of background knowledge, but I also don't want to duplicate for you lots of what's in standard textbooks. So I'm going to try and emphasize some of the newer bits, recent progress, etc. Okay. Of course, I should say one last quick comment, and then this is related to what I just said. You want this structure. These questions, as I phrased them, of course, have been around for like 30 years. So what do I want to emphasize? I want to emphasize new tools. And progress. So I'll try and show you where in recent years we've been able to make things go a bit further than they have before. So beginning with heterotic, I haven't actually posted on the website yet a reading list, but I will do later today, I hope. And another nice reason to start with heterotic string compactifications is that these are the first example from the 1980s, thanks to Candelas, Horowitz, and company, that actually worked out a dimensional reduction of an effective theory and got an interesting looking effective theory in lower dimensions. So this is oldest class of examples fall in this family. See, for example, Candelas et al. From 87. Okay. So beginning then, what are we going to start with? We're going to begin with a 10-dimensional EFT coupled to gravity. And we want to look, for starters, we can upgrade on this at some point, but we want to look at energy scales low with respect to string scale. And the reason I want to do this is that this is where I know the theory the best, so I have the most to say. So let's begin with something that you've all probably seen many times before. Let's look at bosonic part of the 10D action. This could be either the E8 cross E8 or the SF32 heterotic string. I'm going to be more interested in this guy, but they're both valuable. And we have a effective 10D theory that looks something like the following. And I'm going to be pretty schematic with factors of 2, etc., which I will probably get wrong at least somewhere. So there's the bosonic part of a 10D action that should look pretty straightforward. We have various fields, standard curvature term for gravity, a dilaton, heterotic string in 10 dimensions comes equipped with a 3 form that satisfies a Bianchi identity, dh, alpha prime over 2 root 2 is trace r wedge r minus trace f wedge f. And, of course, alpha prime here is one of our expansion parameters in 10D for the energy scales we're interested in, like so. And we have various multiplets, Yang-Mills multiplet, which includes a gauge field valued in one of these Lie groups, and a gaugino. We have Sugrid degrees of freedom, which are a field line. Here, capital Mn are going to be my 10D indices. This is a Novo-Schwarz 2 form, B, a dilaton, gravitino, and dilatino. And let me just say down here that M, N are going to be 10D space-time indices. And capital A here would be a gauge index. Okay. So this is about as easy as it's going to get for a 10D theory. This theory is invariant under, let's see, do I have another there? I don't. Okay. Sure.
I didn't understand your DH equation. Is that an equation of motion?
This is not. This is a Bianchi identity. So just saying that by definition, this 3 form.
Oh, so H has some funny definition.
H is not general.
Oh.
So this is this arises from anomaly cancellation, mixed gauge gravitational anomalies in 10D. So this is a Bianchi identity which relates, the 3 form to the curvature and the gauge field string.
And why is trace f squared have an alpha prime in front?
Great. So there are a whole bunch of different conventions. You can always rescale various fields with alpha prime. I chose these conventions based on the dimensional reduction of heterotic M theory from 11 to 10. These are different than what's in Green-Schwarz-Witten. You can move the factors of alpha prime around. The important thing is that the gauge degrees of freedom, so the field strengths here appear at order alpha prime in the theory. And so you can have the lowest Sugrid degrees of freedom and then the gauge degrees of freedom start at linear order in alpha prime.
I see that. Somehow that's the right way to think about it.
It is a way to think about it. I mean, there's a whole bunch of scales that you can shift around here, but this is consistent up to conformal transformations from what Green-Schwarz-Witten do, if that helps. Other questions? Okay. So importantly for us, this thing is, so S10 is invariant under SUSY transformations, minimal supersymmetry in 10 dimensions. And it respects the following variations. The fermion variations take the form like so. I'm only going to focus on the lowest order terms. They'll be the most interesting. That's 24. And here, good. Where I'm abbreviating, so HM here is a contraction of the 3 form HMNP with various gamma matrices, NP, and the fully contracted version, MNP. And here, my supersymmetry parameter, epsilon, is a 16-component 10D around a Weyl spinner. And the theory will obey supersymmetry so long as it's invariant under all the transformations that I lay out here. What I want to do now is, from the perspective of this theory, I want to look for solutions that are of the form lower dimensional space, lower dimensional maximally symmetric space, cross something. So we want solutions. Just to be specific, I'm going to look for solutions that are of the form M4 cross M6. This is my 10D space. And M4 here, I would like to be some maximally symmetric space. For example, 4D Minkowski space might be nice. And M6, I want to be compact. Now, the reason that having a compact space at this particular juncture is very useful for you is that imagine this like a problem that you got in second year integral calculus as an undergrad. You have some horrible multidimensional integral, 10 of them up there. And if you had sufficient control of all the fields in your problem, if you split up the space, if you're looking for solutions of the form M4 cross M6, if you knew enough about this theory, you could just do 6 of those integrals over the compact space, and you're left with some integral over M4. That will be your action in 4 dimensions. And if you had perfect control, you could write this down perfectly explicitly. So this is the kind of thing I'm after. What more do I need to say about this? I could look for many different types of solution. So I want to consider, to start, consider solutions that preserve some supersymmetry. Preserves some SUSY. I'm going to look specifically at n equals 1 SUSY in 4D, just to be specific. You might say, why do I want to do that? Nature is not manifestly supersymmetric in the 4D universe that I live in, so why impose this supersymmetry? The first pass is that it allows me good control of the effective theory, and it allows me a good way to actually find vacua. So if you're trying to find vacua of any theory in which your solution does not obey any of the symmetry that your theory starts with, these things can be found, but general solution tools are difficult to find. Perhaps you may also be interested in reasons for low-scale or not-so-low-scale supersymmetry. For example, protecting Higgs mass, i.e. hierarchy problems. This choice allows chiral fermions. These are just asides. But there might be interesting reasons that you'd like to look at n equals 1 theories in 4D as well. OK, so we're looking for solutions that respect the symmetry of the form M4 cross M6, which I covered up already. And in order to do that, we have an ansatz. The ansatz will be that we would like our supersymmetry parameter to decompose in the following way. So I need a 4D part and a 6D part to my supersymmetry parameter. And the decomposition I'm looking for here is taking SO19, which is naturally correlated to this guy in 10 dimensions, and I want to break him into SO13 to give me nice 4D spinners, cross SO6. This will take care of my compact 6 out of 10 extra dimensions, and this decomposition will take the 16 of SO19 and break it into a 2, 4. And sorry, can you guys, I guess people said it's a little hard to see down here. I'll try and keep higher in the future. Plus 2 prime 4 bar. So this is just group theory, just decomposing the 16 rep of SO19 into reps of SO13 cross SO6. So this was the choice. Thank you. See? Wisdom. He's only given 1 lecture, but he's already ready. He's like, got the. All right. I think I'm middle. Middle. Okay. So we are choosing to preserve 1/4 of 10D SUSY in this process. So this means of the etas that I started with, that I have here in this decomposition, in order to preserve n equals 1, I need to keep just 1 out of 4. So 1/4 implies that I am interested in keeping just 1 out of 4 etas. Let's call it eta naught. And what I will have then is that fermion variations with respect to now this guy had better vanish in my solution. So I'm interested in delta eta naught psi m written in terms of this decomposition. It will look like so. Theta cross eta naught. And likewise, all the normal terms here. Okay. Gamma Fa eta naught. So I'm just rewriting the same equations, but just making it clear that I'm now interested in just one supersymmetry variation parameter that's going to be important to me for my 4D solution. And as I mentioned also, I'm going to look at M10 being M4 cross M6. And this will tell me this choice, depending on what I want for M4, I can get various classes of vacua that I'm going to hunt for. Specifically, I'm going to look for M4 being maximally symmetric. And as a result, that tells me that the dependence of various form fields, including the 3-form and the dilaton, I want that to not depend on the 4-dimensional space very much at all. So this implies the choice of a maximally symmetric space implies that H mu Mn is 0 and d mu phi is 0, where here I'm splitting up the index dependence. Mu nu are going to be 4D indices, and I'll call ij 60 indices. Okay. Now, following Matt's advice, if I send this one up and bring this one down, pretty good. There we go. Okay. So this leads to, for example, leads to the following. That tells me that the variation with respect to sub eta naught of psi I is going to look like the following. And delta psi mu would be delta mu 4D derivative acting on theta is 0. So I'm just saying I can decompose now my spinor variations in terms of 4D and 60. Yep.
When you say M4 times M6, everything is splitting, or are we allowing warping? Or?
At the moment, I am not allowing warping. This is tricky and heterotic for various reasons. We can come back to that. So if I'm willing to relax the maximally symmetric space, I can start talking about warping. But for right now, that's not going to come up. So proper direct product structure to the full solution. Okay, looking at this guy for a second, there's an integrability condition which tells me that gamma mu nu, grad mu, commutator of 4D derivatives on theta being 0, this actually tells me that the 4D curvature is 0, which tells me that within my class of maximally symmetric spaces, M4 is Minkowski. So I'm going to be looking for solutions where M4 is R13. It's worth mentioning at this point within the space of I'm making choices just to illustrate. If I was willing to relax maximally symmetric, or as Matt just asked, if I was willing to look for warp solutions, etc., there could be other equations that I have to solve. This is just going to be one class of solutions that we're going to write down to begin exploring. So this tells me something about the 4D space. What does this guy, the first variation I wrote down, what does he tell me about the 6D space? So from 1, let's call this guy equation 1. So equation 1, I can write as some sort of derivative operator, 1/8 hi acting on my spinor is 0 to leading order. Now the fact that this is kind of a derivative operator, but not exactly the derivative operator, so something that has been twisted by this 3-form, this is actually quite important to us. So if I had, for example, just covariant derivative in 6 dimensions acting on spinor, this would be the statement that I had a nowhere vanishing covariantly constant spinor, And for those of you that have seen this kind of story before, that means one very particular kind of manifold. But as written, this is not quite that. So the things that I need is that eta naught is nowhere vanishing in order to have the symmetry well defined everywhere in my solution. But it is not covariantly constant because of this H term. So what this type of space that admits a spinner eta naught obeying this equation, this guy gets a name. This is a space M6 which admits an SU3 structure. Again, for those of you that have seen this kind of thing before, if this thing had admitted a spinner without this H term, where it was just covariantly constant, this would be SU3 holonomy. But for the moment, the most we can say is SU3 structure. So let me try and say a little bit.
How is the HI related to the H with
Sorry, this is the H with 3 indices. This is just using, where did I put it? This one? This shorthand notation. Sorry, so the one index H is always just contracted with various gammas. Sorry about that. Any other questions? Yeah.
So, so that's the definition of an SU3 structure. Actually, let me ask you this question. What exactly is the data that enters into the definition of an SU3 structure?
Okay, so we're about to do that in gory detail. There's sophisticated versions. One definition is if you have a nowhere vanishing spinner, solving an equation like that one, that is an SU3.
For any H, without conditions on the H?
Within the heterotic theory, this is going to involve conditions on the H. Within any given flux compactification of string theory, as you're familiar, there will be conditions, consistency conditions on the various form fields that arise. But the general SU3 structure will be something that looks very similar to this. So covariant derivative twisted by form. Yep. This is just to have an n equals 1 solution to my theory in 4 dimensions. So I need the supersymmetry needs to be well defined at every point in the space. The transformation does. Okay, so now let me, the words here SU3 I have not justified. So let me try and say a little bit about where that's coming from. So the rough idea, and we'll start to characterize this more precisely, is what do we mean by SU3 structure? Specifically, where is this SU3 coming from? What we're looking at is the existence of a spinner which is valued in SO6, or transforms under SO6. And this, by basic group theory, is related to the fundamental of SU4. Sorry, the fundamental of SO6 is related to SU4. So we have a local transformation that we can consider. If we begin with our spinner eta on a given patch, so locally, without loss of generality, on a given patch, we can always write it as a 4-vector that has only one non-trivial component. I probably shouldn't have called this chi, not to be confused with the other fermion variations, but bear with me. A number down here. And the reason that this SU3 structure comes up is that a decomposition like this, in order for the spinner to patch nicely over the entire manifold, the transition functions of that manifold have to respect the decomposition that we choose. So transition functions, which take you from patch to patch on M6, will generally, let's write them as Tij, taking you from patch 1 to patch 2, acting on our spinner. We would like this to respect the decomposition we chose. Again, because the coordinates, this is about a local statement for how this spinner should look, not the coordinates that you're using to write it in. So under local coordinate redefinitions on the manifold, you expect this to be true. So generally here, we would expect that T is inside SU4 as written. But because I would like to respect the decomposition I'm choosing from my spinner, here we can say that T will have the form of an SU3 subblock that acts on the zeros that I don't care about. 3, 1, 1, 2, 3. But it'll take the block decomposition of a 1 down here that leaves my chosen direction alone, and an SU3 transformation for the rest of it. Hence, the structure of the transition functions gets reduced from SU4 to SU3. That's where the SU3 comes from.
Why was it SU in the first place?
This was about SO6. So SO6 is the spin group for compact 6 dimension. Okay. So a little bit more formally, again, where does the structure come in? A statement of this type is that if you have a spinner such as I'm describing, this nowhere vanishing spinner, this tells you that the structure group of the frame bundle is reduced from SO6 to SU3. But if you didn't follow that, don't worry about it. We're going to come back and do this a bit more properly. So far we're just warming up. Sure.
The transition function equation, you said you have the same pi on both sides of that. So you're saying you want it to be the same pi? Is that
Yes.
what that means? Okay.
And again, remember, transition functions just take you, so transition functions are defined on the overlap of two patches. I should probably draw this. That's a good question. So if I have a manifold and I come up with some coordinate patches, I can't put global coordinates on compact manifolds in general, but there'll be some overlap of the patches in my atlas. T takes me from the coordinates that describe this guy on one patch to the coordinates that describe it in the other patch, but I'm really describing the same point in the manifold. So I'm saying if locally I get to choose a form of this type, then the transition functions that change my coordinate labels around better respect that. Okay. Random aside, I was just giving some lectures in Germany a little while ago, and they have like the squeegee board, like the car wash German board washing system, which is super cool because the boards get like really clean, but it takes a long time in between each. So at least this is faster. I'm appreciating it now.
We watch them in between every person's lecture with that.
Oh, you even got the squeegee. Cool. Okay. I'm glad I don't have to use it though, because I'm bad at the squeegee. All right. Okay. So far so good. So we've just said, okay, nothing very deep so far. We got a spinner. Great. We got a spinner because we've chosen to look for solutions to the theory that respect a given symmetry. When we do that, we can now characterize something about the manifold that we're choosing as a background, this compact manifold, namely that it has a structure to its transition functions, so they live inside SU3. So to proceed and say more about what this space is and what it obeys, it's going to be useful to us to not have to talk about spinners anymore, but to talk about more general objects on that space. And specifically, I want to build nowhere vanishing, instead of spinners, forms. Forms with various numbers of indices. And I can do that by using the spinner that I have at my disposal. So specifically, I can build a two-form in this case. This is specific to the heterotic. Well, actually, this is more general than heterotic, but I'm going to illustrate it within heterotic. Okay, and sorry, I scribbled that. Gamma 7 here is, as usual, product of gammas in 6 dimensions. And I can build a nowhere vanishing 3-form. Let's call him omega, capital omega, which I can write as omega plus I omega minus, where omega plus, these are 60 indices running over the 6 compact dimensional space. This is minus I eta naught gamma ijk eta naught, and eta naught dagger gamma 7 ijk eta naught. So again, there's nothing terribly deep that has happened here. I just said I have a spinner that I can use to build stuff. What can I do with that spinner? Well, basically the only thing I can do is start contracting them with various gamma matrices and see what I can build. And doing that, I can build something that has 2 free 60 indices, or something that has 3. 2 form and 3 form. So for an argument that these are the only 2 possible things that you can build, I would suggest looking at a paper by Guerrieri et al. From 2002. It has SU3 structure in the title, which I did not write down, sorry about that. But they show that these are the only 2 things that you can have of this type. And of course, because you know a lot about spinors and gamma matrices over 6-dimensional spaces, normalization and Fierz identities on spinors tell you that, in fact, when you write these 2 things down, they have to satisfy a couple of identities. Specifically that J wedge omega is 0, and the maximal form that you can build, so remember this is a 6D space, so if I take a product of 3 2 forms and I integrate it over the space, that's going to give me a number. That number, whatever I get, is going to be proportional to the other way that I could get a top form, which is this one. So taking my omega, multiplying it by its complex conjugate, wedging it with its complex conjugate, and these 2 are related. Okay, so now let's come back to the question that Matt asked, which is, fine, I have an SU3 structure space. What do I do now? Like, that's great. I have something that has a spinor on it. Now I've argued that it has some forms on it. Okay, cool. What else can I do? And it turns out there's a complete classification of how you can characterize an SU3 structure space that I want to summarize briefly for you. And this gets used all the time for various backgrounds of string theory, various compactifications, where you keep form fields, such as the H that I'm playing with here, in play. So this will appear in type 2A, type 2B, in heterotic, etc. And the basic ingredients are all very similar. So my plan is I'm going to show you how to characterize these in the most general possible way. And then we're going to have the exercise of saying, what can we say about how many such things exist? And ultimately, what do they tell us about the field theories? Thank you. Yes, I can. Uh-huh.
Why do we have feathers with the cubic J cube is proportional to the top form?
That isn't an imposition. This is a compact 6-dimensional space, and each of those is a 2 form. So if you wedge them together, you're going to get a 6 form.
Well, why don't you 0?
It could be 0, depending on the form you choose, but I'm just saying it is a number, right? If you integrate it over the space, it'll give you a number, 0, non-zero, whatever. It's just a number. There's a unique, up to scale, there's a unique answer you can get by integrating a 6 form over a 6 manifold. Okay, so now the question is, how can I classify? So we want to be able to say a bit more, and we want to be able to use these forms that I just built to do so. So it turns out there's a cool argument, which is quite lengthy, and I'm not going to do for you here, though I'll show you where to read about it. It turns out that you can phrase the existence of these forms for an SU3 structure manifold in terms of some very general ingredients. So in order to classify, it turns out that the thing we want to do is actually to consider derivatives of these 2 types of forms that I built. And it turns out that you can have things of this type. And let me write this up and then tell you what I mean by this. I heard a question there. Is something closed?
Okay, wait, so
so are you asking where these identities?
Still slightly confused. I'm happy that some Fierz identities imply that equality.
Mm-hmm.
My question, and I agree that any 6 form is pointwise proportional to the volume form, but that proportionality doesn't have to be constant on the manifold.
Certainly not.
Is it constant here?
So the J's in question are nowhere vanishing. So it isn't, the thing that you get from that integral is not constant, but it is constrained.
Okay, so it's not true that J cubed is like a constant times the volume form.
Sorry, no, and I didn't mean to imply that. If it sounded like I said that, sorry about that. No. I just mean that, I mean...
Pointwise proportional.
exactly. Up to functional scale dependence, you have to be getting something proportional. It didn't have to be a constant here. So I see where I may have misled you slightly. As it turns out, the fierce identities show you that it is in this case. Good question. Other questions? OK, cool. All right, so it turns out that you can write, in general, for the derivatives of these two nowhere vanishing forms that I got, you can write expressions that look like this, where this decomposition is unique. This is a big mess, as you can imagine. Proving this is a pain in the butt. Decomposition is unique if the following is true. So if these guys hold, you have a unique decomposition where the Wi are what are called torsion classes. And I will explain the name in just a moment. And they are of a variety of form field types. W1 is a function. W2 and W3 are three forms. And W4 and W5 are one forms. And if you check, that form weighting makes all of this turn out to be right, like, for example, this guy to be a 3 form. OK, super weird. So what are we doing? We're saying that for any SU3 structure manifold, it can be characterized by a set of free forms, 0 forms, 3 forms, or 1 forms, the torsion classes, which give a unique decomposition of this type. So you tell me these forms, which at the moment are pretty much essentially free set of W's. You tell me what those W's are. I can build for you a Hermitian form J and something that is going to be related to a holomorphic 3 form. This will be related to complex structure on the manifold in just a second. A 3 form omega. Now, yep. This is a 4 form. Yes. I'm sorry. Did I write 3 form? Yes, I did. Thank you. 2, respectively 3. Bad notation, but you get the idea. Good catch. OK, so where in the world could something like this come from? So basically, where this is coming from is parameterizing your ignorance. So very loosely, what you're doing is showing that all of these have to transform under the SU3 action that lives naturally on the manifold. These guys have 60 indices over the 6 compact dimensional space. And so they have to transform nicely under this innate SU3 action that we have floating around. So very loosely, just to give you a feel, W4 is a degree of freedom that I can build. So W4 is related to J wedge DJ. This, obviously here I have a 2 wedged A3 form, and the 1 form is the dual of that within the 6 manifold. This guy transforms as a 3 plus 3 bar under SU3. And you can characterize, based on what representations of SU3 it has, whether these things are, how unique these things are. So each of these has a definition that I don't want to get into in terms of J's and omegas. And they're basically induced objects that you can write down associated with the basic 2 form and 3 form in the game. And you can show that these guys will have a unique decomposition and be essentially independent. If these 2 identities are satisfied, you can always write expressions such as this. Is there a question?
So I was just looking at the order. You're saying, given that the Wi's define J and omega, J and omega, unique for both.
So think about this loosely as, you know, if I tell you a function or the derivative of a function, what do you know? So if I had J and omega, I could reconstruct the W's from them. The way that this normally runs actually is to treat the W's as essentially free and then reconstruct J and omega from the W's. Yes. This decomposition, subject to these conditions, this will be invertible in that sense. Good. OK, so why would I be doing this? Why is this interesting? First off, the fact that you can parameterize any solution to an SU3 structure manifold by these 5 torsion classes is kind of cool. So you give me 5 forms, and in principle, any torsion classes I choose, I can find some SU3 structure manifold that will be defined by those. It'll have a different J and omega that are topologically distinct that will have different properties. Also, in ways that we'll see, the WIs directly influence, so lead to pieces of the effective field theory in a big way. I'll give you some examples of this in just a second. So they basically characterize for you different properties of the n=1 theory that we're going to have. So the fluxes are normally associated to having the non-trivial form field backgrounds in the first place. So in the heterotic string, as I've set this up, that would be the non-trivial H in the compact directions. You're right that they're correlated. So you could define the form fields via the torsion classes, but they are not normally what you refer to as the flux itself. Let me say just briefly why they are called torsion classes at all, because that's not totally obvious. Do I want to go this way?
Yeah, no, that was right.
That was right. Good. So why do I call these guys torsion classes? There's a variety of ways to think about this. You can phrase this either in terms of the connection on the tangent bundle of the manifold itself, or perhaps a way that's more familiar to you if you've taken GR, is that this 2 form Jij is quite closely related to the metric on the space. So specifically, again, something that will be familiar to some people who've seen things in Kähler geometry, you can show that J as a 2 form can be related in complex coordinates. I'll just rebar with an I. This is just an aside. So basically, the way that you define this Hermitian form is correlated to the existence of a Hermitian metric in complex coordinates. I haven't told you anything about complex coordinates yet, but just bear with me. The same thing also works in a variety of forms for real coordinates, which is what I've been working with here. And associated to that metric, of course, you can write the commutator of covariant derivatives acting on a vector. This looks like Riemann curvature acting on the vector plus torsion acting on gradient of vector. Very schematically, right? This is a familiar thing, hopefully, from your GR class. And what you can show is that so long as the W's are non-zero, you will have non-trivial torsion associated to this connection, i.e. associated to this metric. So this will not be a torsion-free connection for the gravity part of the theory that you have in play. Hence the name torsion classes.
You said the torsion is associated with the metric. I usually think of the torsion being associated with the connection.
That's right. I mean, I'm giving, so if you demand that these covariant derivatives be metric compatible with this metric, this is what you get. There are 2 ways to think about it. If you're also happier, you can just think about this innately as the tangent bundle to the manifold is carrying a connection in the normal GR sense, and that guy has torsion. So whichever way is more familiar with you. I agree that it's better to think about it in terms of the connection. Okay, so far everything I've said has just been general for SU3 structure. And aside from this decomposition, which is kind of interesting, I have said only that I can pick these W's and I can have some nasty differential equations that I have to solve for a J and omega, and then I have to tell you something about the manifold and then the physics from there. In order to proceed a bit further and a bit more explicitly, I want to now specialize. So this is just about SU3 structure in general. I want to specialize to the heterotic case, which I started setting up for you, in order to be a bit more explicit. So let's go back to heterotic. So within the heterotic string, this was solved in complete generality. So the same steps that I did asking for a maximally symmetric space, building these form fields out of the spinner, this was solved by Strominger in '86 in complete generality, and hence the solution that I'm about to write down is referred to as the Strominger solution in the heterotic context. This is the most general n equals 1 supersymmetric solution of the 10D heterotic string that will lead to an n equals 1 4D theory. I will also reference for you, so Strominger's paper from '86 is valuable. I would also suggest checking out Lopez et al. This is HepTH 021118, I think. These guys rewrite the Strominger system in terms of the modern language that I've phrased here in terms of torsion classes. Strominger writes it in a little bit different language just in terms of J and omega. And what Strominger showed, phrased in this modern language, is that we need the following. We need W1 and W2 to be 0, W4 to be related to a half W5, and moreover to be exact, and W3 to be free. So if you have these torsion classes within your solution, then it will solve the equations of motion that I put on the other board. For the fermion variations, you will have a good n equals 1 solution to the heterotic vacuum. Okay. Yeah. Not directly. Asking about Stiefel-Whitney classes is a great question. We're going to talk about other topological invariants in the manifold in just a second. At the moment, these are just forms that live over the space, so they're not related to any particular topology. We'll start constructing bits of topology in just a moment. Other questions? Yeah.
So all of this that we've discussed so far is independent from the gauge bundle.
Great, so I've totally ignored the gauge bundle. We're going to come back to that, but yes. So far, I've even ignored the equation of motion for the gauge bundle. We're going to come back to them, but I'm just doing the spinor variations that constrain the manifold to start. And I should say, this particular set of torsion classes is what I need for an n equals 1 solution to heterotic. This kind of thing can happen in any string compactification. Again, whether it's M theory, type 2, etc. You'll be able to phrase the existence of a solution as a set of conditions on the torsion classes for any SU3 structure manifold. Okay.
Then if I give you a set of W's that obey those, you're saying it's kind of clear that there exists a J and W satisfying all of those equations? Or
Okay, so there's a number of steps. So if you give me a set of W's, I have to actually solve differential equations for these two guys to find them, which I may not be able to do. But in principle, I could try and search for a J and omega then that gave me the right-hand sides.
you're saying they don't necessarily exist?
They do exist, but whether I can find them is another question. So in principle, they exist. There will be, and you do have a uniqueness statement that given a set of W's, you will have a unique J and omega that correspond to them. In practice, this is differential geometry, and it's a pain in the butt, and I may not be able to solve it. Then I could ask, can I work backwards and then show that I solve all my equations of motion? I'm not doing that for you here, but you can see, if you check out, for example, Strominger or these guys, you can see that this set of torsion classes within these differential equations does solve your equations of motion. And you can do that for any type of string theory that you choose to look at. And this has been done, I should say, by the way, for type 2 M theory, etc.
Yeah, after this step, so you don't need to assume that it's Taylor, right?
I have not assumed it's Kähler. I haven't even shown you it's complex. And in general, it's neither. So these are really problems in differential geometry. For general torsion classes, this is not a happy manifold in any sense that those of you that have taken differential geometry before might hope for. Not Kähler, not complex, just not nice. Just some random 6 manifold that has some forms on it. Though Yinan's question is exactly where we're going to go next, which is how do we find the allowed J's and omegas, and what allows us to actually get some traction on characterizing these solutions. I'm missing one.
The Lopez et al. Paper is 021118.
Thank you. That's a lot of ones. I still get thrown by the fact that the archive in the new format switched from the last 4 digits to 5 digits 2 years ago, and I'm always leaving off one still.
I'm still thrown that it's not this format. 10 years.
Okay. So our question is, now, given the W's, or in principle, if you had some or you allow them to be free, how to find J and omega. And then, of course, what does it mean once you got them? So once you got them, what else can you say about the manifold and eventually the physics? Okay. I should say that your options here, so how might you do this? You could try to solve, for example, for the possible spinners, A and a naught, and then plug in. That might be something one could try. This is hard. You can try to restructure the SUSY equations of motion in terms of J omega, or perhaps just the torsion classes themselves, and then search for constraints on torsion classes. And this is really, so when I gave you the solution here for the Strominger system, this is how progress was made. So you can rewrite your equations of motion to phrase everything in terms of W's, and then you can get some traction. So specifically, in the heterotic context, this last one led to, and again, I'm not showing you the details of this because it's long, but just stating the result, the following. So I mentioned that these were exact. In fact, what arises from the heterotic equations of motion is not just that it's exact, but that it's exact as a derivative of the dilaton. And you find that W3 is free in the heterotic Strominger system, but it can be related to choice of H. So this is related to the question before, can I think of the torsion classes as like fluxes? Not exactly, but if you give me a torsion class, I can construct the non-trivial H that satisfies the equations of motion, i.e. I can find the flux on the background, or given a choice of flux, you can fix the torsion classes in terms of it. Okay, another just quick illustration within the heterotic theory. I said that these guys actually contribute to the torsion classes, contribute to the effective theory in a big way. As one example of that, just bring this up a little bit. Another example in the heterotic context of where these torsion classes come in, the Gukov-Vafa-Witten superpotential in the heterotic context takes the form of W related to omega wedge H plus I dj. And you can show that in this context, after solving the equations of motion, the dj is essentially omega 1, and the H in question is related to the dual of W3. So just as an illustration of how does this affect your theory, in the n equals 1 superpotential, you tell me the torsion classes, I give you the superpotential. We'll see more details of this in a moment, but this is just a flavor of what's to come. Okay, now, how do we go further? So how do we say anything more meaningful about these manifolds? So it's worth noting at this stage that some of the geometry you've probably seen so far before can be phrased in terms of simple choices of torsion classes. So if the torsion classes are more simple, you're going to have a wider toolkit to be able to characterize the geometry. Yep, I did that wrong again.
No, that's all right.
That's okay.
Pull down the front one.
Pull down this guy. I'll take it. I will totally take it. Okay. So to get us back into the realm of geometry that we may have seen before, a brief aside is it can be demonstrated that if W1 and W2 are 0, then you will have a complex manifold. And if dj is 0, this corresponds to a Kähler manifold. So we can see already from the choice of solutions to the Strominger system that W1 and W2 are 0. So in general, the n equals 1 solutions to the heterotic string will be complex manifolds. That's useful. But DJ is not in general 0 for what I've written here. And these guys will not be Kähler. OK, so here, one other comment. Omega can be always described as a 3-form. That can be written, and I haven't defined this notation. I'll show you more about this in a minute, but just for those of you that have seen it before, it's going to be written as a global section of a particular antisymmetric power of the dual tangent bundle. This is just saying there is a way to characterize, in terms of the underlying geometry, where this guy lives. And the fact that it's nowhere vanishing tells you that this antisymmetric power of the cotangent bundle must in fact be trivial. So the fact that its global sections are not allowed to be 0 anywhere, this tells you that this must be trivial. And this tells you that the first Chern class of your manifold has to vanish. So this is related to the question that I had a little bit ago about what can you say about topology of the manifold now based on the torsion classes. So the existence of the nowhere vanishing 3-form actually tells you that you have C1 equals 0. The first Chern class, and I should say, by the way, this, if you haven't seen this kind of geometry before, this is just related to the trace of the Ricci tensor, has to be 0. Not Ricci flat. Ricci itself does not have to be 0, but its trace does. OK, this is important. Mathematicians frequently use just this property alone to characterize whole families of geometry. We want a little bit more than that, but it'll be interesting to come in. So the question now is, OK, cool. I need a solution to the Strominger system of this type. I know it's a complex manifold. I don't know much else about it. I know it's 6-dimensional complex manifold. What solutions are known? Here's the big question. OK, so what solutions can I find? Well, the simplest one that you have all seen at least once before, if you're sitting in this room, is the first class of examples is ones for which all the torsion classes are 0. W5 is 0. In this class of backgrounds, you can argue that the flux is 0. Hij itself must be 0. The dilaton has to be constant, because remember, one of these guys was related, whoops, I covered it up already, but this exactness was d of the dilaton, so the dilaton must be constant. And that tells you that from our equations of motion, our nowhere vanishing spinner has to actually be covariantly constant. And of course, this tells us that I have a manifold of SU3 holonomy, thanks to Berger's classification. And Susie, at lowest order in alpha prime, ignoring the gauge bundle still, tells me that this also gives me Rij is 0, i.e. the manifold is Ricci flat. Good. So, this guy we have seen before. Something that is Ricci flat SU3 holonomy, of course, has its very own name, and at least one Fields medal associated to it. This is a Calabi-Yau manifold. And you've probably seen this definition before, but let's just write up the equivalent definitions just to be precise. A CY manifold is compact for my purposes, complex because W1 and W2 are 0. It admits a unique Ricci-flat connection, Ricci-flat Kähler metric, let me phrase it that way. Kähler metric, written in terms of complex coordinates because this is a complex manifold. Only the 1, 1, barred, unbarred components of the metric are non-zero. And thanks to Yau in 77 and 78, he proved Calabi's conjecture that these properties, as I've written them, is one-to-one with SU3 holonomy, C1TX being 0, and Kähler. Yes. Yeah. I mean, there is a unique Ricci-flat metric. You can always shift up to various harmonic representatives, but yeah. Okay. So just to put this in context, Yau won a Fields Medal for this because part of this direction is easy and part of it is really hard. So the hard part about this is not a constructive proof. So in order to really show that you solved the equations of motion, I argued that I needed to show there was a Ricci-flat metric on this space. What Yau showed is that if you work out other properties, for example, C1 of the tangent bundle to this space being 0 and the manifold being Kähler and SU3 holonomy, that this confluence of much simpler properties tells you that a Ricci-flat metric exists. It does not build said Ricci-flat metric for you. And in no cases, no non-trivial cases, do we explicitly analytically know of non-trivial Ricci-flat metrics on Calabi-Yau threefolds, which is the case I'm considering here. Various people, myself and Matt Hedrick, among others, have worked on numeric approximations to this kind of problem. There's various tools you can try and get at to pin down the metric, but it is a source of great difficulty that we don't explicitly have metrics, even though, thanks to Yau, we know they exist. Okay, so one class of solutions to the Strominger system are Calabi-Yaus. Again, I'm ignoring the gauge bundle so far. I'm going to have to come back to that in a minute. But certainly, for the compact six-dimensional space, Calabi-Yau manifolds satisfied that portion of the equations of motion. And I can now ask, how many of them are there? How many examples, distinct examples of this type do I have? And there is greater than 500 million known examples. And I can actually go further. This is not just known Calabi-Yau manifolds. This is actually known solutions to the Strominger system. So one choice of solution in this case that's always available to you for the Strominger solution is to choose the gauge connection equal to the spin connection on the manifold, i.e. to choose your gauge bundle to be the holomorphic tangent bundle, and that will give you a solution for every one of these Calabi-Yaus. So all of these will solve my effective theory that I wanted, and they'll give me a lot of different examples. Great question. Not at all yet. I'm going to talk about what is starting to be known about that in a moment. So finiteness and being able to characterize and bound the possible solutions is very important. But at the moment, we do not have an answer to that question.
We've got about 3 minutes left.
3 minutes left. OK, perfect. I'm at a good stopping point. So let me just mention one other non-trivial class of solutions that's known. And you're going to get a flavor for where we're about to go. So 500 million of that type. Actually, I'm just going to leave this here because I'm running out of time. Let me just plop that one down. And then say one last thing. There is one other interesting class of solutions to the Strominger system known, which are non-Kähler and non-Calabi-Yau. And just to give you a sense of how difficult this is once we leave Kähler and complex geometry behind, EG2 is the so-called Fu-Yau construction. And the basic idea is that gentlemen's Goldstein and Prokushkin, can't spell his name, Prokushkin, wrote down a solution for the 6 manifold, M6, which has the form of a product of 2 S1s fibered over a K3 surface. I'll describe more about this in a second, in such a way that the total thing is non-Kähler. And this was in hepTH 0212307, hopefully with the right number of digits this time. And then Fu Yao added gauge bundle. So they added the F to this solution. And what they find is a 2-parameter family so this is basically 2 distinct topological classes as opposed to 500 million examples. So 2 versus 500 million. And unfortunately, all have small cycles, including potentially the overall volume. So these are actually, although they satisfy the equations of motion that I've written down, it is not clear that they are consistent with the expansion that I've chosen for the 10D theory. So I chose to look at scales small compared to the string scale. I wanted the overall volume. I want my alpha prime expansion to make sense. And in this limit, generically, these solutions break down. So I'm going to stop here, and I'll continue tomorrow. But what I want to show you is the reason that this gets so hard. So the reason that we can go from 500 million examples known to 2, which kind of fails, is because this is a problem in algebraic versus differential geometry. And as we all know from high school, solving algebra problems is a lot easier than solving calculus problems. So what I'm going to do is start exploring the so-called easy class and trying to answer the question that Matt raised, which is what is actually known about that first? And we'll come back to features that we can then use to extrapolate to the more general class, which is hard to solve. So I'll pause there, and we'll take up tomorrow morning. Questions? Yeah.
When you say S2 autonomy, you mean exactly S2 autonomy?
Yes, not reduced. Sorry, are you asking, like, could it be smaller than SU3? Yeah, I mean, in principle, that is not forbidden here, though, of course, that will add to increased supersymmetry. So I can always, go back to n equals 2 solutions from this by sort of reducing things further. But yeah, I'm looking for proper n equals 1 solutions in what I've written here. So exactly SU3 holonomy.
No non-Taylor compactation that have really self-confused.
No.
No, but there are papers on this.
Yes. I mean, people, so that's a great question. So there are lots of papers written on this, and people take various tactics, including I've had some papers of this type too. So things that you can do is you can say, I don't know any really good examples, but what can I say about the properties of the theory for any geometry? So for example, I worked on trying to talk about the moduli space of these theories independent of an example. So there's a lot where people have tried to write down, sort of general structure they can extract. In terms of explicit examples, I'll talk a little bit more tomorrow about this. There is actually one other new class that came out earlier this year where several mathematicians actually claim to have an infinite family of non-Kähler Strominger solutions. As I'll explain, they also forgot some physical constraints that matter. So short answer is no, there is no fully physically satisfying Strominger system solutions for non-Kähler heterotic compactifications. There are examples where you relax the maximally symmetric space. So some people have looked at examples of domain wall type solutions with SU3 structure backgrounds, and there that you can find good, valid, full compactifications, but not Minkowski. Yeah.
So usually when we look at the existence experience like this on a manifold, we have to think about Stiefel-Whitney, which is what George said. Why did we not think about that here? I
mean, you certainly can phrase things in terms of what the Stiefel-Whitney class. I'm not saying it's independent. I'm just saying it doesn't determine things for you that you want. So, I mean, vanishing Stiefel-Whitney class is related to the C1 equals 0 condition on this manifold, which will be satisfied. So it's true. You do have a good Stiefel-Whitney class and it works, but and that is true for any SU3 structure. So I probably should have made that clear. But it is not by itself enough to reconstruct everything else. Okay.
I wanted to ask you more about these
Sure.
classes.
Mm-hmm.
So I guess the first, your mic's still on, by the way.
Before I start answering questions.